Welcome to the video Help with Physics Problems for Physics 1B. This video is going to cover Homework Set 6, Part 1. There's no heading for this section. For 1221 students it covers questions 1 to 8, including the past exam questions, and for 1231 it covers questions 1 to 13, including past exam questions. Problem 1. In this problem, we're told that the work functions for lithium, beryllium and molybdenum are 2.3, 3.9 and 4.2 electron volts respectively. We're asked what are the maximum energies and velocities of photoelectrons produced by incident light with wavelength 350 nanometers. So to answer this, we're going to have to use the equation HF is equal to the work function plus the maximum kinetic energy. This comes about from the photoelectric effect. A photon with energy HF strikes the metal. The metal requires an amount of energy equal to the work function to eject an electron, and the remainder of the energy is transferred into kinetic energy of the electron, among other things. So this gives us the maximum kinetic energy of the ejected electron. So what we need to do first of all is work out what energy this incoming photon has. We have its wavelength, so we can use that to work out its energy. We know that c is equal to f lambda because it's a wave with velocity c, and so this tells us that the energy is equal to hc over lambda, which is equal to 6.626 times 10 to the minus 34 times 3 times 10 to the 8 over lambda, which is 350 times 10 to the minus 9, and so the energy is equal to 5.68 times 10 to the minus 19 joules. Now, to get this into electron volts, because our work functions in electron volts, we divide this by the charge on an electron, 1.602 times 10 to the minus 19, and when we do that, we get 3.55 electron volts. And now, for lithium, we were told that the work function was equal to 2.30 electron volts. So this number is larger than this, so it's got enough energy, the photon has enough energy to eject an electron from the surface of lithium. So now the maximum kinetic energy is equal to the energy of the photon, 3.55 minus 2.30, the energy needed to eject it, which gives us 1.25 electron volts as the maximum kinetic energy that the electron can have. We're also asked to find its speed, so we've got a half mv squared. This is kinetic energy is equal to 1.25. Now we need to convert this to joules, so we times it by 1.602 times 10 to the minus 19. That's the charge on the electron E. And solving this, we have v squared is equal to 2 times 1.25 times 1.602 times 10 to the minus 19 over the mass of an electron, which is 9.11 times 10 to the minus 31. So solving this tells us that v is equal to 6.63 times 10 to the 5 meters per second. Now the work function for beryllium is equal to 3.90 electron volts, and the photon coming in only has 3.55 electron volts, and so the photon coming in does not have enough energy to eject an electron from the surface, so no electrons are ejected. For molybdenum, the work function is even higher, 4.20 electron volts, so we've also got no electrons are ejected. Problem 2. In this problem, we're told that a hydrogen atom is in the first excited state, which is the n equals 2 state. What is the maximum wavelength of a photon that can ionize it from this state? So lambda max is equal to what? So what we need to do is work out how much energy we need to put in to remove the electron from the n equals 2 state. To remove it from n equals 2, we have to move it to n equals the infinity state. This is when it's left the atom. So one way to do this would be to use the Rydberg equation, but that's not provided to you on the formula sheet. So let's do it with formulas that are provided on the sheet. So we've got that the energy of a state, of the nth state, is equal to minus me to the 4 over 8 epsilon naught squared h squared times 1 on n squared. So our change in energy when we're going from n equals 2 to n equals infinity is equal to this at infinity. 1 over infinity squared is 0, so that's 0. So it's minus e2, which is just the negative of this, so it's me to the 4 over 8 epsilon naught squared h squared 1 over 4. This 4 is 2 squared, so 1 over 2 squared. So now what we need to do is just substitute the numbers and solve this in to give us our energy. So we've got 9.11 times 10 to the minus 31, that's the mass of an electron, times 1.602 times 10 to the minus 19, or to the power of 4, over 8 times epsilon naught squared, which is 8.85 times 10 to the minus 12 squared, times h squared, which is 6.626 times 10 to the minus 34, squared times 1/4. So solving this on the calculator, we get 5.45 times 10 to the minus 19, and that's in joules. And so this is the energy that the photon needs to have. It's the minimum energy. If a photon has more than this energy, then it can also eject an electron from the n equals 2 state. So we've got E is equal to hf, which is equal to hc over lambda, and this is equal to 5.45 times 10 to the minus 19, and so lambda is equal to hc divided by this energy, so 6.626 times 10 to the minus 34 times 3 times 10 to the 8 over 5.45 times 10 to the minus 19, and solving that on the calculator, we end up with 365 nanometers. So that's the answer to this problem. Now we're on to problem 3. And this is a 1, 2, 3, 1 only problem. In this problem we're told NASA is considering solar sailing, using the momentum of light and of massive particles emitted from the sun to help push a spacecraft equipped with large diaphanous sails. Assume that the density of the material from which the sails are made is about 1,000 kilograms per meter cubed, so about the same as water. So the density is 1,000 kilograms per meter cubed. In part A, we're asked what is the minimum thickness of a sail such that the use of the momentum from the sun's light is enough to balance the gravitational attraction of the sail alone towards the sun. At the Earth's orbit, which is at an orbit of radius 150 million kilometers, so times 10 to the 9 meters, the solar constant, or intensity of solar radiation, is equal to 1.4 kilowatts, so 10 to the 3 watts per meter squared. Okay, so what we've got is we've got sails with a certain thickness T. And we have particles coming in and bouncing off them. Now, from the impulse equation, we know that the force times time is equal to the change in momentum, and so this tells us that the force is equal to the change in momentum, which will be, if we have an initial momentum p, this will be 2p, because we've got p minus minus p, and this is over the time. Now we know that the energy is equal to the momentum times the speed of light. So we can replace this P with E over C. Now energy over time, that is power. So we've got 2P over C. And we know that intensity is equal to power over area. So we can replace this power with 2IA over C. And we've got the intensity And so we can work out the force per unit area using this equation. Now this is the force that's pushing it away from the sun. So here's our sun. This is the force pushing it away. Let's call this the radiation force, so F rad. So F rad's going that way, and we're told that this is balanced by the gravitational force pulling it back towards the sun. So the gravitational force is given by G times the mass of the sail times the mass of the sun over the distance squared. So what we need to do now is equate these two things. So we've got this is equal to 2IA on C. And what we're trying to do is solve for the thickness. So let's substitute in for the mass of the sail. We know it's got a thickness T and it's got this density. So the mass is equal to the density times the thickness times the surface area. So we've got G rho TA times the mass of the sun over RE squared is equal to 2IA on C, and our surface areas here cancel out. And so to solve for thickness, thickness is equal to 2I over C times the radius of the distance from the sun squared over G rho T times the mass of the sun. Sorry, that T's already here. We don't have this T here. And RE is standing for the distance from the sun. So we've got 2 times 1.4 times 10 to the 3 times 150 times 10 to the 9 squared all over 3 times 10 to the 8 times G, which is 6.67 times 10 to the minus 11 times the density, which is 1000, times the mass of the sun, which is 1.99 times 10 to the 30 kilograms. So solving this on the calculator, we end up with 1.56 times 10 to the minus 6 meters. So the answer is equal to 1.6 micrometers. So there's our answer. Now in part B, it says, how does the answer depend on distance from the sun? Okay, so we've got a squared dependence up here, but we've also got a dependence on the intensity. And you should remember from Physics 1A that intensity drops off as 1 on the radius squared. So we've got an inverse R squared relationship in this I and an R squared relationship here. So those will cancel each other out. And so part B, there is no dependence on the distance from the sun. Problem 4. This is for 1, 2, 3, 1 students only. We're told that singly ionized helium, like hydrogen, has only 1 electron. However, the nucleus is different. So in the helium nucleus, we've got 2 protons and 2 neutrons. And we've got a single electron orbiting it here. So we've got a charge of plus 2e here and a charge of minus e here. In the Bohr-Sommerfeld model, what difference does the extra nuclear charge make? Well, this is going to mean that there's a stronger electrostatic force. Instead of being the force between E and E, we'll have the force between E and 2E. Have a look at the derivation of the energies and spectral lines for hydrogen, and then determine how the energy levels and spectral wavelengths for singly ionized helium would differ from those for hydrogen. Okay, so we know that the total energy is equal to the kinetic energy plus the potential energy, which is equal to 1/2 times the electron which is moving. It's the electron's energy that we're considering. So this is 1/2 times the mass of the electron times the velocity of the electron squared. And now this potential energy is a negative energy. It's given by minus Ke times this charge times this charge. So this will be 2e squared over the radius. So that's the radius of the atom. So this is our energy equation. Now what we should also do is consider the forces involved. In the Bohr-Sommerfeld model, we assume that this is undergoing circular motion. So the force, the resultant force, will be mv squared on r, and this force is exerted by the electrostatic force. So this resultant force needs to be equal to the electrostatic force, which is Ke. Now it's the two charges multiplied together, so E times 2E, so times 2E squared over r squared. And this is the mass of the electron here because it's the electron which is undergoing the circular motion. So let's substitute MEV squared into this equation up here, the energy equation. And so we've got that the total energy is equal to, okay, we can see MEV squared R. This R will cancel with one of these R's. So we've got a half from this half times Ke 2E squared over R. These 2's will cancel out, and then we subtract off the Ke 2E squared on R. We've still got this term. And so solving this, we have Ke E squared on R minus 2 Ke E squared on R, which gives us minus Ke E squared over R. Now for hydrogen, this energy is equal to minus Ke E squared over 2R. Now, one of the postulates of the Bohr-Sommerfeld model is that standing wave solutions are the only solutions. So 2 pi r, the circumference of the orbit of the electron, has got to be equal to n lambda for the electron. And then from de Broglie's equation, we know that lambda is equal to h on p, where p is the momentum. And so we can write this as nh over mv. And so now rearranging this for r, you can see that r is equal to nh over 2 pi mv. Now what we want to do is get rid of this v dependence here. So let's go back to this equation here. And we can write v squared is equal to Ke times 2E squared over MER. And so let's substitute in for this R here. So we've got Ke times 2E squared over Me times 2 pi mv over nh. And so this v will cancel with one of these v's. So we end up with v is equal to Ke times 2, 4, because we've got 2 times 2, E squared pi me, or these m's will cancel, so that disappears, over nh. Now for the energy expression here, we actually want R, so let's substitute this V back into R. So this is the blue one, we substitute this into the blue one, and we have R is equal to nh over 2 pi me times the inverse. So this is nh over Ke 4 pi E squared. And so this is n squared h squared over 8 pi squared me E squared times 1 over Ke, which is times 4 pi epsilon naught. So we could write this as n squared h squared epsilon naught over 2 pi me E squared. Okay, so finally what we can do now is we can substitute this back into our energy equation up here. And that tells us that our energy is equal to minus Ke, which is 1 over 4 pi epsilon naught, times E squared over R. So we've got 2 pi me E squared over n squared h squared epsilon naught And so solving this pi and this pi will cancel out, this 2 will cancel with one of these, and we end up with minus me to the 4 over 2 epsilon naught squared h squared times 1 on n squared. So this is equal to 4 times minus me to the 4 over 8 epsilon naught squared h squared times 1 on n squared. So it's 4 times that of hydrogen. So the energy levels are 4 times higher, and it also asks us to determine how the spectral wavelengths would be different. So we've got E is equal to HF, which is equal to HC over lambda. Now if we've got the energy being 4 times as big, we've got lambda is equal to HC on E, so the wavelength is a quarter as big, it's 4 times smaller than for hydrogen. So E is 4 times larger, lambda is a quarter of lambda for hydrogen. And that's how you solve this problem. This is problem 3 for 1221 or 5 for 1231. In this problem, we're told that the failure of the Bohr-Sommerfeld model was one of the stimuli for the development of the quantum mechanics. But what is wrong with the Bohr-Sommerfeld model? The Earth goes around in circles around the Sun and doesn't fall into it. Why should an electron in a classical circular orbit fall into the nucleus? Okay, so the Bohr-Sommerfeld model basically says that the electrons go around the nucleus in circular paths, that as they're going around in a circle they don't lose energy, and that the circular paths which have standing wave solutions are the only stable ones. Now the problem is that it just states that these electrons don't lose energy, but accelerating charges radiate energy. So this implies that over time, electrons traveling in a circular orbit should lose energy, which is going to make them, they should eventually spiral in towards the nucleus. But this doesn't happen, so that's a problem with the model because it doesn't explain why this doesn't happen. Now, in terms of the Earth, so the Earth is not charged, so it does not lose energy through radiation in this manner. Now, the Earth does have mass, and it is predicted that it should lose a small amount of energy through gravitational radiation, but this hasn't been observed yet. And the energy it loses through radiating gravity waves is much, much lower than the energy lost by an accelerating electric charge. Okay, we're on to the past exam question. This is from 2003 and it's question 4. So the question says, UNSW astronomers have discovered a cloud of interstellar gas. The gas has exactly the same absorption spectrum as normal atomic hydrogen. However, from the motion of the gas in known magnetic fields, the astronomers determined that the atoms are positively charged. An early theory which proposed that the gas is made up of He plus ions is discarded. First, the spectrum has the wrong wavelength. Second, the charge to mass ratio of the atom is much, much too small for helium plus. Eccentric cosmologist Joseph Lupus proposes that each of the atoms is in fact a small uncharged black hole of mass m. So we've got a small uncharged black hole of mass m at the center, about which a normal proton, so here's our proton with a proton mass much less than the mass of the nucleus, follows a circular orbit. Lupus's model resembles the Bohr-Sommerfeld model for hydrogen, but because the nucleus is uncharged, the attraction in this new atom is purely gravitational instead of electrostatic. Okay, so this is going round in a circular orbit. Your job is to calculate the mass m of the black hole and the radius r, so here's our radius, of the orbit necessary for this atom to have the same absorption spectrum as normal atomic hydrogen. So part 1 of the question asks us to derive the relationship between the radius r of the orbit and the speed v of the proton in the gravitational orbit around mass m. To do this, we're going to have to consider the forces. The only force acting on this proton is the gravitational force from the black hole here. And so that force has got to be equal to the resultant circular motion force. So the circular motion force is given by mv squared on r, and this is equal to the gravitational force, which is g little m, where little m is the mass of the proton, so let's give that a subscript p, times the mass of the black hole over the radius squared. And so this will cancel with that will cancel with that, and we end up with v squared is equal to gm on r, which tells us that v is equal to the square root of gm on r. So that's what part 1 was asking us for. Part 2. Use the de Broglie wavelength. So the de Broglie wavelength, lambda, is equal to h over p, to derive an expression for the values of the radius of the orbit at which the de Broglie waves for the proton give constructive interference. Okay, so this is one of the postulates of the Bohr-Sommerfeld model, that we've only got the standing wave solutions. So this tells us that 2 pi r has got to be equal to n lambda. So that's the postulate. So what we're going to do now is substitute into this. So we've got 2 pi r is equal to n h on p, which is equal to nh over the mass of the proton times the velocity of the proton. Now what we're trying to do is get the radius, so we can write the radius is equal to nh on 2 pi mp, and then we've got this 1 on v. So we can write the 1 on v as r over gm to the 1/2. Okay, so we've got the square root of r here, and we've got r here. So let's square everything. So we've got r squared is equal to n squared h squared over 4 pi squared mp squared times r over gm. This r and this r will cancel out, and we end up with r is equal to n squared h squared over 4 pi squared mp squared g times capital M, which is what that part of the question was asking for. Now part 3. Using the above result or otherwise, determine the required mass m such that the spectrum of this atom has the same wavelength lines as normal atomic hydrogen. The ground state of normal hydrogen is minus 13.6 electron volts. You may use without proof the expression for the gravitational potential energy of two masses m and big M and little m at separation r. So we're told Ug is equal to minus g mm on r, and that the energy of a circular gravitational orbit is Ug on 2. So that tells us that the energy is Ug on 2, which is a half of this, so that's equal to g big M little m over 2r. And we want this energy, the gravitational energy, to be equivalent to the ground state energy of the hydrogen. So this is equal to minus 13.6 electron volts. So now all we need to do is solve this equation here to try and get the mass m. So we've got the mass m is equal to 13.6. Now that's electron volts. Let's get it into joules. So we times it by E to get it into joules, and then we times it by 2r, and we divide it by G times the mass of the proton. Now R is given by this expression here, So this is equal to 13.6 E times 2 over G times the mass of the proton times n squared. This is the ground state, so that's 1. So it's h squared over 4 pi squared mp squared G now times m. So let's put this as m squared. Okay, so now all we need to do is substitute in the numbers. So we've got that the mass squared is 13.6 times 1.602 times 10 to the minus 19 times 2 times h squared, which is 6.626 times 10 to the minus 34 squared over. Now on the bottom we've got g squared, which is 6.67 times 10 to the minus 11 squared. And then we've got the mass of the proton cubed. So the mass of the proton is equal to 1.67 times 10 to the minus 27 cubed times 4 pi squared. And so solving this on the calculator, we end up with the mass is equal to 48 times 10 to the 6 kilograms. So 48,000 tons is the mass at the center of this atom. Okay, we're up to problem 4 for 1221 or problem 6 for 1231. In this problem we're told that in a particular shower, raindrops have a diameter equal to 4 millimeters and are falling at 10 meters per second. In part A, we're asked what is their de Broglie wavelength. This is given by lambda is equal to h over p, which is h over mv. So what we need to do is work out the mass of this raindrop. So the mass is equal to the volume times the density, which is equal to 4/3 pi r cubed times the density of water. So just substituting in, we've got 4/3 pi 2 times 10 to the minus 3 cubed times 1,000 kilograms per meter cubed. And solving this, we get 3.35 times 10 to the minus 5 kilograms. So now we can substitute everything in here. H is 6.626 times 10 to the minus 34. The mass is 3.35 times 10 to the minus 5, and the velocity is 10. So solving this, we get 2.0 times 10 to the minus 30 meters. So that is a very small wavelength. Atoms are of the size of about 1 angstrom, so 10 to the minus 10 meters. Part B, would they form a diffraction pattern if passed through a narrow slit? Explain your answer. Well, the problem is that you couldn't make a slit narrow enough for them to pass through. The slit would have to be wider than 4 millimeters to let them through, but that is orders and orders of magnitude above their wavelength, so they're not going to diffract. So no, it is not possible to have a slit large enough for them to pass through while being narrow enough to cause diffraction. Okay, so might be a good idea to just state some numbers. This would have to be greater than 4 millimeters, and this would have to be of around about this order. Okay, so that's how we can answer that one. Okay, we're up to problem 5 for 1221 or 7 for 1231. In a colour TV, the accelerating voltage for the electrons is typically 20 kilovolts. So V is equal to 20 kilovolts. Whence the warning sign on the back. What is the de Broglie wavelength for these electrons? So we've got lambda is equal to h over p, which is equal to h over mv. So what we've got to do is work out how fast will an electron be going once it's been through this potential difference here. And so if we can assume it starts from rest, it's going to gain energy passing through this voltage difference, and that energy will be in the form of kinetic energy. So we'll have a half mv squared is equal to the charge on the electron times this, the voltage it goes through. So times 20 times 10 to the 3. And so our velocity is equal to 1.602 times 10 to the minus 19 times 20 times 10 to the 3. And we need to times this by 2 and divide it by the mass on the electron, which is 9.11 times 10 to the minus 31. And so we take the square root to get our velocity, and this tells us that the velocity is 8.38 times 10 to the 7 meters per second. So now what we can do is we can substitute into here. So we've got 6.626 times 10 to the minus 34 over 9.11 times 10 to the minus 31 times 8.38 times 10 to the 7. And solving this, we get 8.67 times 10 to the minus 12 meters. So that's around about 9 picometers as the wavelength. Okay, we're up to problem 6 for 1221 or problem 8 for 1231. We're told that green light has a wavelength of 550 nanometers. And we ask, what is the speed of an electron with the same wavelength? So V of an electron, and what voltage is required to accelerate it to that speed? So we know that lambda is equal to h over p, which is equal to h over mv. So we want our wavelength to be 550 nanometers. And this is equal to 6.626 times 10 to the minus 34 over the mass of the electron, which is 9.11 times 10 to the minus 31 times its speed. So solving this for the speed, we end up with the speed is equal to 1,322 meters per second. So that's about 1,300 meters per second. And then we're asked, what voltage do we need to accelerate it to this speed? Well, we consider energy. In this case, it gains kinetic energy, and it gains that from the electrical potential energy, which is given by E times V, where capital V here is the voltage. So this tells us that the voltage is equal to a half times the mass of the electron, which is 9.11 times 10 to the minus 31, times the velocity squared, over the charge on an electron, 1.602 times 10 to the minus 19. And solving this, we get 4.97 times 10 to the minus 6 volts. So this is around about 5 microvolts. Okay, problem 9. This is a 1231 only problem. In this problem, we're told the following variables may have standing wave solutions. We've got psi in quantum mechanics, and we know that psi star psi is equal to the probability of finding a particle in a given volume. We've got E, the electric field magnitude, and we know that E squared is equal to it's proportional to the electric field intensity. And in acoustics, we've got the acoustic pressure P, and P squared is proportional to the sound intensity. Compare and contrast psi E or P in terms of their interpretation and detection. Psi star psi is used in quantum mechanics, and it's usually used when the probability is very low, so when we only have a few particles. E squared and P squared are used when there's lots of particles, and so when we're really looking at a statistical situation where we're looking at the averages of what's happening with these particles. To detect E squared, we use an antenna. To detect p squared, we'll use a microphone. And to detect psi star psi, we'll use a particle detector. This is a past exam question. It's from 2005, question 5. The first part says, sketch the principal elements of an experiment involving light that demonstrates an effect associated with waves. Name the effect and explain very briefly what happens and why this demonstrates wave-like properties. Okay, so we can do something to do with diffraction or something to do with interference. Both of those are common wave properties. So let's choose Young's double-slit experiment because it's got diffraction and interference. So here's our double slit. And here's our screen, and we'll get an intensity pattern on the screen like this if we just consider the interference, and it'll look more like this if we include the diffraction as well. So Young's double slit experiment demonstrates both interference and diffraction. Light passing through the two slits interferes, giving a series of maxima and minima in the intensity on the screen. So there we go. Now part 2 says, sketch or give a brief description of an experiment involving light that demonstrates an effect associated with particles. Name the effect and explain very briefly what happens and why this demonstrates properties normally associated with particles. Probably the easiest effect to choose is the photoelectric effect. In the photoelectric effect, we have a photon coming in with energy hf, and it can eject an electron as long as it has enough energy. So we have hf is equal to the work function plus the maximum kinetic energy of the ejected electron. And this is an effect, the photoelectric effect, generally associated with particles, as if a photon does not have an energy greater than the work function of the metal, it cannot eject an electron. Now, if this was a wave, you would expect that the atom sitting here could wait some time and absorb a number of different waves until it had enough energy to eject this electron. But this isn't what we see. There is a cutoff frequency, and if the photons do not have enough energy, no electrons will be ejected, no matter how long you shine the light for. Okay, we're up to problem 7 for 1221, which is problem 10 for 1231. And it says the excited states of hydrogen are unstable. They decay after a finite time. Consequently, their energy cannot be determined with arbitrary precision. The lifetime of the n equals 2 state is about 10 nanoseconds. And this is only about. Use Heisenberg's uncertainty principle to determine the maximum number of significant figures that may be used when expressing its energy. So Heisenberg's uncertainty principle tells us that the uncertainty in the energy times the uncertainty in the time is greater than or equal to h bar on 2. So we know that the uncertainty in the energy has got to be greater than or equal to 6.626 times 10 to the minus 34 over 4 pi, because it's 2 times 2 pi, times this 10 nanoseconds. And so this is equal to 5.27 times 10 to the minus 27 joules. Now what we need to do, this has given us the absolute uncertainty in this energy, but what we need to do now is work out the energy so that we can get the number of significant figures. So the energy is equal to minus me to the 4 over 8 epsilon naught h squared times 1 over n squared. Now, we know that this thing in here is equal to 13.6 electron volts. So we can write this as minus 3.4 electron volts. Or you could just substitute in for all of these if you want. And then we need to convert this into joules. So times 1.602 times 10 to the minus 19. So our uncertainty in the energy over the energy is equal to 5.27 times 10 to the minus 27 over 3.4 times 1.602 times 10 to the minus 19. So this is equal to 9.67 times 10 to the minus 9. Now this is the part which is important. This tells us that we can't represent the energy to more than around about 9 significant figures. After 9 significant figures, the uncertainty is going to have a similar magnitude to the actual value. Problem 8 for 1221 or 11 for 1231. In this problem, we're told that gamma rays can be produced by the relaxation of a nucleus in an excited state. In principle, we could measure the uncertainty, i.e. the bandwidth, of the gamma rays produced, and from this measure the lifetime of the excited state. Typical lifetimes are a few picoseconds. For a gamma ray of energy 1 mega electron volt, with what precision will we need to measure the spectrum? i.e. we're meant to work out what delta E over E is equal to. So we've got E, so we've got to work out the uncertainty in E. So we can use Heisenberg's uncertainty principle that delta T is greater than or equal to h bar on 2. So we've got that delta E is similar to h over 4 pi delta T. And we're told in the question that the average lifetime is of the order of picoseconds, so 10 to the minus 12. So delta E is approximately 6.626 times 10 to the minus 34 over 4 pi times 10 to the minus 12. So solving this, we get 5.27 times 10 to the minus 23. So delta E over E is equal to 5.27 times 10 to the minus 23 over 1 mega electron volt, which is 10 to the 6 times 1.602 times 10 to the minus 19. So this is approximately 3 times 10 to the minus 10. So this gives us the precision. This is problem 12, which is a 1, 2, 3, 1 only problem. In this problem, we're told that a musician plays a note at a nominal 55 Hz, so the frequency is 55 Hz, for 1 second, so it lasts for 1 second. And we're asked, what is the uncertainty in the frequency? So we know that delta E, delta T is greater than or equal to h bar over 2, which is h over 4 pi. And this is from Heisenberg's uncertainty principle. Now, we know that E is equal to hf. There's no uncertainty in Planck's constant, but there is an uncertainty in the frequency. So we can write this as h delta f delta t is greater than or equal to h over 4 pi. So cancelling out the h's, we end up with delta f delta t is greater than or equal to 1 over 4 pi. So we know that delta F is greater than or equal to 1 over 4 pi delta T, which is approximately 1 over 4 pi times 1 in this first case where the note lasts for 1 second. So the uncertainty in the frequency is at least 0.080 Hertz. Now we're asked, what is the uncertainty if the time is 0.10 seconds? In that case, we've got that the uncertainty in the frequency is at least 1 over 4 pi times 0.10. So this is 10 times bigger than that one. So this is equal to 0.80 Hertz. Now problem 13, which is a 1, 2, 3, 1 only problem. We're told that in Young's double-slit experiment with light of wavelength lambda and slits of width A and separation D, the interference pattern intensity is given by I of theta is equal to I naught cos squared pi d sine theta over lambda. So this part's the Young's double-slit part, and then the sine alpha over alpha squared, this is the diffraction around the slits part, where alpha is equal to pi a sine theta over lambda. And we're told in the Young's experiment with electrons, a total of n electrons are detected on the screen behind the two slits. How do you interpret I theta for electrons? Well, I theta is equal to the number of electrons arriving at an angle theta on the screen. And so to work it out, we know that between minus pi on 2 and pi on 2, I theta d theta, we get all these n electrons. So this is equal to n. So I theta is the number of electrons which arrive at each angle. And then it says, how could you calculate I naught? The question doesn't ask us to actually do the calculation, just how we would go about doing it. So what we would do is we would put this function into this integral here, and we can then solve it to work out what I naught is, as long as we're given d, lambda, and a. And then it says, if you covered one of the slits, what sort of pattern would you expect? So you then expect just to get the diffraction part. So this part would cancel out. So we'd have I of theta. Now we'd only have half the initial intensity because only half of the electrons are getting through. So we'll have I naught on 2. We won't have the interference part. We'll just have the sine alpha over alpha squared. So this would be the diffraction pattern that we would expect if one of the slits was covered.